All right, during our last video, we looked at custom peptide synthesis, and I ended on kind of a glum note. I said that the greenness is terrible, it has high cost, it takes a lot of time, the yield is low, and some of these drugs that are custom polypeptides cost like $30,000 a year. So scientists have been working hard to automate as much as possible. The first breakthrough came in the 70s with a guy named Merrifield, and Merrifield ended up winning the Nobel Prize, I think in 1984, for his design to basically automate some of these processes. And so what he did was he created a polystyrene resin. So this whole group is a polymer, it's just polystyrene, and we've got these leaving groups on the bottom down here, right? So we've got these chlorine groups coming off of some of these aromatic molecules. So in this system, you basically got this leaving group embedded on a plastic. What you can do is get one of your amino acids. And as you can see, this amino acid is already Bach protected, right? So they've just made a bottle of Bach protected amino acid. And what you can do is flow this through this little reactor, and this carboxylate will just go and do SN2 chemistry on any available chlorines that it can find, right? So it's just going to do basic SN2 chemistry. And when that happens, you're able to form this new covalent bond. So we've got a new covalent bond here and here. All right, so you keep on flushing this through until all of those chlorines are replaced with amino acid residues. All right, but at this step, what we need to do is we need to remove our Bach protecting group so that we can then add in our next amino acid. So if you remember, to remove this Bach protecting group, what we have to do is react it with trifluoroacetic acid. That's the strong acid that's used to kind of kick off that entire protecting group. So now what we have is we've got this amino acid kind of dangling off of our polystyrene resin. Let me clean this up a little bit. And now we've got a free amine on there as well. All right. Typically though, because we're treating this with TFA, this amine coming off the end is actually going to be protonated, right? But not a problem. In fact, it'll work in the next step anyways. So now what we do is we react this with our second amino acid. And again, our second amino acid will just kind of flow through this system. So it's going to have a Bach protecting group. It's going to have an NH, and it's going to have a free carboxylic acid, and then it's going to have an R group down here. In fact, let me move this arrow down a little bit. And these won't just react together. Like we said in the previous video, this carboxylic acid won't just react with the amine on its own. We need a peptide coupling reagent. So that's when the DCC will be used as a reagent. So basically, during this entire step right here, we're going to flow through DCC and our Bach protected amino acid that we want to be amino acid number 2 in our polypeptide. So after this step, we'll link them together and we'll have a dipeptide. Right? And then if we want to remove the Bach protecting group kind of coming off the end here, you can probably predict what will happen next. We can react this with trifluoroacetic acid, remove that protecting group, and then if we want another amino acid, we can say, all right, let's add in Bach protected amino acid number 3 plus DCC. That's our peptide coupling reagent, and basically repeat this process again and again and again and again, multiple times over. And then our final step is to treat it with hydrofluoric acid. And what this hydrofluoric acid does is this is the last step to kick off the polypeptide chain. Meaning, if we think about what was going on here during this whole process, right? From step 1 to that last step, we still were attached to this polystyrene resin here. We want to eventually kick this peptide off so that we could use it as a drug, for example. So by treating it with hydrofluoric acid in the last step, you can get your free polypeptide. All right, so this was really cutting edge at the time. It really lowered the cost and made this somewhat practical. It's still expensive, obviously. Like I said, that HIV drug is still $30,000 using techniques like this, but it allows you to make it a little bit more manageable from a chemistry perspective. The cool thing with this is this method for a long time kind of had a maximum of about 50 amino acids that you could do. After that, things kind of started getting gummed up. It wouldn't work very well. But just this year, in 2020, a group from MIT started looking at this method in more detail, and they made what's called a flow reactor, where basically it's entirely automated, it runs at high temperature, avoids a lot of the problems with the Merrifield method, and now we're able to make polypeptides that I think are 168 amino acids is what was reported in their paper. In addition, they're learning how to fold these polypeptides into essentially proteins by using additional chemistry. So even though this is a method that was pioneered in the 1970s, really it's still continuing to grow and expand, especially as we're learning more about these protein-based drugs and polypeptide-based drugs. So really that's where we're going to end today. In fact, that's where we're going to end for the year. But I did want to show you the summary reactions for this chapter. So if you go to the end of the chapter, we saw how to synthesize amino acids. We said that these first three methods, kind of shown up here, weren't the greatest because they're not enantioselective, meaning you would get a mixture of R and S stereochemistry for your side chains. So it requires a lot of work to purify your amino acids this way. The more modern technique is to use the enantioselective synthesis using a chiral catalyst. By doing that, we're able to produce one enantiomer almost exclusively and not have to lose half of our product due to this scrambling of our stereocenters. If you ever work in a biochemistry lab, usually you just buy these directly from a manufacturer, but there are situations where you might want to make unnatural amino acids, in which case you would still do a method like this. And then in the last few videos, we saw how to make custom peptides, right? So how do we make a peptide bond? Well, we need a peptide coupling reagent like TCC. However, that's still not good enough. We still need to protect the ends we don't want to react. So we said in some cases we need to protect our amine, and in other cases we need to protect our carboxylic acid. But if we put on a protecting group, we also need to ensure that we can remove that protecting group at the end. So each of these has their own specific protecting group removal strategy as well. All right, that's basically it for this chapter. If you go in the textbook, there's a bit more talking about proteins. However, we're really limited on time, so I'm really going to stick with the basics of amino acid synthesis and peptide synthesis. Good luck studying.